Okay. Uh, Hi, this is Manikishan, and this is my another attempt at reading this paper, the case of 4-bit precision k-bit inference scaling laws. This is as a part of a course paper reading, but I'm also developing this habit of reading more papers and logging it online. So let's see. So the format is going to be the same as the previous video. We have some questions to help us to diagnose this paper or dissect this paper and get the required data from it or information from it, and these are the questions that I want to answer, and uh, I want to cover as much as the paper can, and I'm sure I'm not that much familiar with most of the terms, so we'll be noting that, and later I'll be searching that out, what's them and all. So that's it. Let's dive into it. Sorry. I Yeah. So the paper starts talking about quantization. So according to them, sorry. Uh, so basically, quantization methods reduce the number of bits required to represent each parameter in a model. Yes, trading accuracy. Sorry, trading accuracy for smaller memory footprints and inference latencies. So I think what they are saying to say is by quantization we reduce the number of bits required to represent each parameter by trading accuracy for smaller memory footprints and inference latencies. Okay, we are trading accuracy so that we get smaller memory footprints and inference latencies. This is more, we need this because nowadays models are becoming very huge with lot of billions and millions of parameters that are going to be there. Uh, and However, the final model size depends on both the number of parameters and of the original model and the rate of the compression. Yes. For example, a 30 billion 8-bit model and a 60 billion 4-bit model have the same number of bits but may have different zero shot accuracies. A zero shot accuracy is when we don't pre-train the model again, first accuracy. In this work, we studied this trade-off by developing inference scaling laws of zero shot performance in large language models. Study this trade-off by developing inference scaling laws. Okay, of zero shot performance. Okay. We are trying to develop inference scaling laws of zero shot performance in large language models to determine the bit precision and model size that maximizes zero shot performance. Okay, basically they're trying to see what's the breakpoint or what's the optimal combination for the model size you want, the compression you want, and the bit size you want. So we run more than 35,000 experiments with 16-bit inputs and k-bit parameters to examine which zero-shot quantization methods improve scaling for 3 to 8-bit precision at the scales of 1900 MB to 90 million to 176 billion parameters across the LLM families, Bloom, OPT, NeoX, and GPT-2. We find that it is challenging to improve the bit level scaling trade-off, with the only improvements being the use of a small block size, splitting the parameters into small independently quantized blocks, and the quantization data type being used. Overall, our findings show that 4-bit precision is almost universally optimal for total model bits and zero shot accuracy. So what they're trying to do, what the problem is, why is the problem important? I think we'll have to read introduction more to know that better, but let me write that down. So what they are trying to do, the paper is Inference scaling laws. Short LLMs to determine which combination of bit precision and model size maximizes the zero shot performance. Spoiler, for precision is the best. Uh, Turns out to be the best. So, introduction says large language models are widely adopted for few shot inference. Okay, let's see what's zero shot. The other terms, trivia. First one, zero shot inference. So zero shot doesn't mean we're not training it again. So they say zero shot learning is a two-step process that involves training and inference. During training, a model learns about labeled set of data samples. During inference, the model uses auxiliary information to classify the new set of classes. So what does one shot mean? Smaller number of Okay, one shot learning is an objective categorization for most in computer science. Okay, few shot learning. So what does few shot mean? So this is zero shot learning. So few shot few shot learning aims to emulate the human ability to learn from a mere handful of examples. Let's get a better understanding. Okay. So basically, zero shot doesn't include fine tuning, meaning the model tries to do the task with its general mm, understanding of language language context, etc. So basically, from what I understood, zero shot learning, few shot learning. Zero shot learning is when you have a model which is already pre-trained, and for a given task, you don't train it again and again. Uh, you won't do fine tuning to it. Directly give the task and see how it works. That's zero shot directly. And few shot learning, you give a few handful examples for it to uh, learn that niche or nitty-gritties of that task it's meant to do, and after that it might perform better. Maybe image classification, all these things might need some few shot to see. uh, like if you to want it to learn specific things, so it will learn. So that's zero shot, few shot. Okay, back to the paper. Inference, but they can be challenging to use both due to their large memory footprints. Yeah. However, both memory and latency are primarily determined by the total number of bits in the parameters. Therefore, if you reduce the model bits through the quantization, you can expect the latency of the model to reduce proportionally, potentially at the expense of end task accuracy. Yeah. So, a model size and its latency depends on how many parameters it have. In turn, how many model bits it needs to store all these parameters. So, if we can reduce these bits, number of bits per parameter using quantization, we can expect the latency of the model to reduce proportionally on how much we are increasing, but at the expense of an end task accuracy. Since we can quantize the parameters of a trained model to an arbitrary bits precision, a trained model bit precision, this raises the question of how many bits should be used to optimally trade off accuracy and the total model bits given our current base methods for model quantization. So they're not giving any better quantization methods, but they are trying to see how many bit precision we need basically. What's the optimal thing? For example, if we have a 60 billion LLM in 4-bit precision and a 30 billion LLM in 8-bit precision, we achieve which will achieve a higher accuracy. To study such trade-offs, it is helpful to take the perspective of scaling laws, which evaluate the underlying trends of variables to make generalizations beyond individual data points. Okay, take the aspect of scaling laws which evaluate the underlying trends of variables. In this paper, we study bit level inference scaling laws for zero shot quantization to determine the precision that maximizes zero shot accuracy given a certain number of total bits in the model. So that's what we have wrote, right? We study bit level inference scaling laws for zero shot quantization to determine the precision that maximizes accuracy given certain number of database. Okay, our main finding is that 4-bit parameters yield optimal performance. We study 5 different model families: OPT, Pythia, Pythia, NeoX, GPT-2, Bloom, Z. with 19 million to 176 billion parameters and for 3 to 16 bit precision. In addition, we run more than 35,000 zero-shot experiments to vary many of the recently studied advances in quantization precision, including the underlying data types and quantization block size. We find that reducing the precision steadily from 16 to 4 bits increases the zero-shot performance for a fixed number of model bits. So, for a fixed number of model bits, if you keep reducing the precision from 16 to 4, it keeps on increasing. While at 3 bit, the zero shot performance decreases. This relationship holds across all models studied and did not change when scaling from okay, making 4-bit quantization universally optimal, all case tested. Okay, so I think that's what they're saying. Total number of bits, total model bits, and this accuracy. So if you see 16-bit accuracy, okay, accuracy kept increasing. So everything kept increasing, but what does this mean? Mean accuracy. So the 4-bit has highest accuracy for all the quantizations at any point. But the third bit is not high, but it's fluctuating. So this is for OPT. So leading 4-bit precision to be the best precision. Beyond this, we analyze. Okay, let's write this. Is aiming at inference scaling laws. Solution quantization. Why are they using scaling laws? Because because it's helpful to evaluate underlying trends of variables to make generalizations instead of beyond. That's it. So beyond this, we analyze which quantization method improve and which degrade bit level scaling. Beyond this, They also analyzed which quantization methods improve and degrade the bit level scaling. How to see what scaling laws they might mention it. So let's see. We find that none of the quantization methods we test improve scaling behavior for 6 to 8 bit precision. That's right. Okay. Then for 4 bit, data types and small quantization block size are the best ways to enhance bit level scaling. We find the quantile quantization and floating data points data types are the most effective, while integer and dynamic exponent data types generally yield worse scaling trends. Okay, for most 4-bit models, a block size between 164 to 128 is optimal to in our study. It's a block size. From our results, we can make straightforward recommendations for using zero-shot quantized models for inference. So their suggestion is that their recommendation is always use 4-bit models with small box size and with a floating data type. And this is the best. If trade-offs in total model, sorry, yeah, if trade-offs in total model bits or predictive performance are decided, keep the precision in 4-bit but vary the number of parameters of the model instead. Okay, so they're saying keep the precision of bit precision to be 4, but increase the model size if you want better predictive performance. So while earlier work has shown that it is possible to significantly improve the predictive performance of quantized models by using outlier dependent quantization, we show that this is not effective for bit level scaling. In particular, we analyzed instabilities in 3-bit OPT and Python models and show that while these models can stabilize through an outlier dependent quantization, which we term proxy quantization, this does not improve bit level scaling compared to 4-bit precision.